Yeah, now the cluster features are actually used by one of the first algorithms for stream processing or for stream clustering that uses this online-offline framework, which is CluStream, a variant of k-means. Yeah, so the cluster features are used to make or transfer k-means like stream clustering, or k-means to a stream-like clustering method. The cluster features from above are a little bit extended, namely by the information of the time slots when the points in X have arrived. We'll see right in a minute why. So if XY has arrived at TI, we simply store, in addition to the traditional cluster features, which are those three here, the number of points in X, the linear sum of the points in X, the squared sum of the points in X. In addition, those two things here, which is LSTX, is the linear sum of the time slots of X. So all the time slots of the points are summarized in LSTX, and the SSTX is then the squared, it should be read squared sum of the time slots, obviously. In X, this formula is correct. Yeah, so all the time slots of the points when the points in X have arrived are summarized or are summed up linearly within LSTX and squared within SSTX. Yeah, and again, still the additive property of these new cluster features are still maintained. So we still have this property that there's the CF, the temporal clustering features, they are called actually temporal cluster features. The temporal clustering feature of an set X can easily be maintained by adapting or absorbing an additional point by just simply adding the points property to all those sums. Yeah, so n is just increased by 1, LSX is just LSX of LSX plus p, SSX is just SSX plus p squared, and the time slot of p is just incorporated here, just added to LSX, and the time point where p arrived squared, so to the power of 2, is just added to SSTX, and that's it. Yeah, so still the maintenance is extremely efficient. Yeah. So now, how is CluStream working? So just a brief overview first. So the general idea is that a fixed number of microclusters, the parameter here is Q microclusters, are maintained over time, and all the microclusters are represented as temporal cluster features by those 5 values here. Yeah, so for each of the Q microclusters, we maintain the 5 temporal cluster features. The whole thing is initialized by applying k-means with k equals to x to q, of course, now. So it's q-means over an initial buffer, and then the summary structures are built for all the q clusters we get here. Yeah? So both q and the buffer, the initial buffer size, are obviously input parameters that you have to set. But okay, and then upon request you can run k-means on a snapshot of the QC temporal cluster features you have at that moment. Yeah, so snapshot means you just say, okay, give me the snapshot at time point t17. So you get all the temporal cluster features valid at that particular snapshot at that particular time point, and then you can run k-means on the Q temporal cluster features. And obviously Q should be more or larger than K in order to make sense. You know? So Q should be a larger number. Of course, this is again a trade-off between more detail and less efficiency. Yeah? So between accuracy and efficiency, obviously, because if you set Q too large, then we will see that you have to compare a newly incoming point with all existing cluster features. So you have to compare this, the new incoming point with all Q cluster features, temporal cluster features. So if Q is large, efficiency drops, obviously. If Q is small, then you probably merge too many details. So the abstraction level is too coarse. So the accuracy is decreased in that case. Okay, so now the online phase of CluStream. So you maintain Q cluster, microclusters, temporal cluster features, and you do so by adding new observations from the stream. Yeah, so new observations from the stream came in. X, Y is the new observation, and what you do, you find the closest microcluster according to the distance you use. Yeah, so you compute all the distances of the point coming in. The new observation is coming in to the cluster representatives, the mean values, which can be computed easily from the temporal cluster features, obviously, of each of the microclusters. So you also work with a distance threshold, but this distance threshold is now dependent on the standard deviation of the cluster. Yeah, so if the distance, so you find the closest one, if xy is closer to the mean, to the representative, than alpha times the standard deviation of this cluster, then you say that x fits to this microcluster and you add it. Yeah? If not, you don't look at the second closest microcluster, you just create a new microcluster containing only xy. So this is very similar to the leader algorithm, but it's now a little bit more sophisticated, a little bit more adaptive, because you use as a distance threshold the standard deviation of the microclusters. Yeah? And if you create a new cluster, since you only want to maintain a fixed number of microclusters, so if you add a new microclusters, you end up in having Q plus 1 microclusters, which is not what you want. So you delete a microcluster by using one of the following actions. You delete the least recent microcluster if the least recent microcluster has a relevance timestamp of TR, which is smaller than, actually smaller than T now. T now is the TI actually, yeah, the timestamp where X appeared. So your current timestamp minus a threshold. So if the relevance stamp of the microcluster, whatever that is, we will see that below here, is longer ago than a given threshold, then you delete that. If no microclusters are, because you think that this microcluster is then outdated. If no microcluster is outdated, then you simply merge the two closest microclusters in order to get, again, Q microclusters. Okay. Yeah, so as I said before, it's very similar to the leader algorithm. The only difference so far is that you have, well, you maintain the number of microclusters doesn't grow as in leaders, so you always maintain only Q microclusters. So this is new, and the other thing which is new is what I told you before, is that the threshold is adaptive. It is visualized down here. I'm sorry for that, because this is really a little bit annoying or confusing, because it says T here, but actually that should visualize exactly this idea here, that if the point is alpha times standard deviation closer to the mean, so this is the standard deviation, and then alpha times standard deviation, if it's closer to the mean, you are okay. The cluster absorbs or takes this new observation. If not, if it's here, somewhere here, it creates a new microcluster, and then you have this deletion or merging action down there. Yeah, for the deletion, we talked about that. We need this relevance stamp saying if the microcluster is outdated already or not. So this timestamp should approximate the average time, or not only should, but approximates the average timestamp of the last M objects of this microcluster. And it's just computed as the time of the arrival of the M times 2 times N, M divided by 2 times N nth percentile Yeah, so n is the number of points in the microcluster, and m is another parameter. So you look at the time in the distribution of time slots of MC, of this microcluster, of which you compute the relevance stamp for. So that's why it looks a little bit like this one here, but anyway. So you look at the time of arrival of this percentile here, which is, oh, there are some brackets missing, I'm sorry for that. So there's a bracket missing down here, and there's a bracket missing down here, which is just 1 minus m divided by bracket 2 times n and bracket, yeah, of the timestamps in the microcluster. So the denominator is 2 times n, of course, of this fraction here. Okay, so anyway, this relevance stamp should give you an idea if the whole thing is outdated, because if this percentile here is smaller than the current timestamp minus a threshold, which is another parameter, then you think, or you classify this microcluster as outdated and you delete it. But only if you have to delete a microcluster in order to maintain just Q. Yeah, that's the idea. Yeah, and in the offline phase, then you can use at any time for any snapshot actually of the microclusters. So you can use k-means. So the snapshot of the microclusters are stored. In this case, the authors propose a pyramidal time frame. So we talked about that before. And now, given k and a time horizon h, you locate all valid microclusters within this horizon, and the final clusters are then computed by just using k-means, a little bit modified in terms of the microclusters over certain time horizons are treated as pseudo points, and you use a little different initialization. So seeds are not picked randomly, but just sampled with a probability which is proportional to the number of points. Distances are calculated between centroids of the microclusters, of course, because you don't have the raw data anymore. New seeds are weighted by the number of points, the k clusters obtained from applying k-means on those representatives of the microclusters are then called macroclusters, because in the online phase you say you maintain a micro view, and in the offline phase you create a macro view from the micro view, so to say. Yeah? So that is the basic idea and the basic way of working of CluStream. So here is a short discussion. So it's a single scan again. Algorithm stream compression is done using microclusters. It views the stream as a changing process over time. So and this is in contrast than just viewing or doing the clustering of the whole stream at one time. It can characterize clusters over different time horizons in a changing environment. So you can compute the clusters in the offline phase for any time horizon you want, and in that case you can somehow also find pattern evolutions. However, only entire clusters are aging, because here you only compute or you only delete entire microclusters and not individual points. So the aging is only for entire microclusters. Should read microclusters here. Noise handling can be done or has to be done offline, so there is no online noise handling. Q is fixed, and of course it should be much larger than Q. There are a lot of parameters. We talked about that. So we have the horizon here in the offline phase. In the online phase, we have this tau, and we have this alpha, and we have this m. So there are a lot of parameters to set, but that's how it is. And again, model inherent limitations such as sensitive to noise and so on and so on. But at least a k-means version of for streams.